and Assalamualaikum everyone. Today our group gonna present a report of center of pressure. This is our teammate. For the introduction part, the pressure center is a point of on a surface immersed such as skate in a particular liquid. This point represents the effect of the fluid pressure force on the surface immersed. In the case of the submerged surface horizontally, the water pressure is distributed horizontally, symmetrically, and is passing through the surface area center immersed. So, in the case of the surface immersed vertically or inclined at a certain angle, the center of the sum of water pressure force is under the center of area immersed, and this pressure increase as the depth increase. For the objective, first to find the water pressure force which affecting a regular rectangular plate. Second, to find the water pressure center, the position of the point of the water pressure force affecting on the plate. And lastly, to find the tracheal moment which resulting from the water pressure through balancing the device by placing the weight at the other end of the device and comparing the calculation with the required result. For the scope of experiment, this experiment focused on determining the center of pressure on a plane surface submerged in water under static condition by using a 500 gram of weight to measure balancing moment. The study aimed to validate the theoretical equation for the hydrostatic force and center of pressure. The scope includes the measure of relevant parameters such as surface dimension, submerged depth, and fluid density, ensuring accurate comparison of theoretical and experimental results. For theory or working principle part, this is all the formula that we use in calculation.
So this is our apparatus for the center of pressure experiment. So next, this is our methodology. For the first, we need to wipe the quadrant with a wet rag to remove surface tension and prevent air bubbles. And then we need to place the apparatus on a level surface, indicates that the base is horizontal. And then place the balance arm onto the pivot and ensure that the balance arm swings freely. And then the fourth is we need to hang the weight and place at the end of the balance arm. And then the balance arms need to balance. Next, we add 50 gram to the weight hanger. And then add the water in the tank slowly. And then add more water or drain valve at the end of the tank. It's open until the balance arm is aligned with the center mark of the level indicator. And then record the height of water display on the side scale of the quadrant in unit millimeter. And then repeat the step 5 until 8 by adding 50 gram weight each time until reach 400 gram. And then remove one by one weight and take the reading for the second reading. And then after finish everything, we need to open the drain valve to release the water.
For the result, as you can see, we have done 8 tests. So we have divided by 2, 4 tests by 4 tests. So partially submerged got 4 tests. The mass is 0.05 kg until 0.2 kg. For fully submerged, the mass start from 0.25 kg to 0.4 kg. Okay. For the hydrostatic force for partially submerged, the equation will be 1 over 2 rho g b d square. And for fully submerged, the equation will be rho g b big D and then d minus big D over 2. For the center of pressure for partial submerged, the equation that we use is mgl over f, that will can be uh, say by 2 ml over rho b d square. So for fully submerged, the equation will be ml over rho b d in d minus d big D over 2. For the theoretical center of pressure, for the partial submerged, we use h over d over 3. And for fully submerged, the equation will be d square over 12 plus d minus d over 2 power 2 over d minus d over 2 plus with h and minus with d. By using the value from the first table and also use the equation that we have seen, we can get all these value from the equation.
So this is the first graph that we have to plot, that is the hydrostatic force versus the deformation. And we can look at this graph. More the hydrostatic force, there is more of that of motion. The graph is increased based on the hydrostatic force and depth of motion. So next, the second graph, the experimental depth of central pressure versus depth of motion. So we can look at the graph has decreased. So the low, so the low depth of motion, the low experimental depth of central pressure. So this the graph that we have got is a theoretical depth of central pressure versus depth of diffusion. So we can look at here. So when the depth of motion increase, the when the depth of motion decrease, the theoretical depth of central pressure increase. So this is the question that we have to discuss on the variation of hydrostatic force with depth of emission. So hydrostatic force is the force exerted by a fluid at rest on the immersed surface. Its variation with depth of immersion is governed by the equation force equal to rho g ah, where F is a hydrostatic force, rho is a fluid density, g is a gravitational acceleration, a area of surface immersion, and h depth to the center of submerged surface. So, as the depth of immersion increases, the hydrostatic increase linearly. This is because h minus the depth to the center increase, leading to proportional increase in F. Additionally, large area A and higher fluid density rho amplifies the force. So the first question of our discussion is discuss on the relationship between depth of the center pressure and the depth of motion. So the depth of center pressure Fc is the point where the resultant hydrostatic force acts on a submerged surface. It is determined by the formula Fc equal to H minus plus Ig over Hp, where is H depth to the center of the surface. Ig is second moment of area about the horizontal axis passing through the center and area of the surface. So the relationship indicates that as the depth of immersion increases, the depth of the center of pressure AC approaches H, because the term Ig over HA becomes smaller. This means for very deep immersion, the center of pressure is nearly considered as the center. For shallow immersion, however, the difference between AC and H is more pronounced. So, the last question that I have to discuss: compare and explain the discrepancy between the experiment and theoretical result for the central pressure. So, first of all, we have to look at the theoretical basis. Theoretical calculation assume ideal conditions such as perfect fluid, no viscosity, uniform pressure distribution, and accurate geometry measurement of the surface. So, for the experimental observation, in practical experiment, discrepancies can arise due to surface irregularity, variation in the shape or roughness of the surface may lead to deviation from assumed geometry. Measurement error: small error in measurement the depth, area, or fluid density can affect the result. So for the comparison, theoretical results provide idealized, simplified view based on precise formula and assumption, but for the experimental result reflect the real-world condition, often differing slightly due to the factor mentioned above.
Next, safety procedure for this experiment. First thing, we need to handle the weight carefully to prevent falling on the feet, and then make sure the eye must be perpendicular when taking the readings to prevent parallax error, and then adjust the equipment's feet to ensure that it is enough balanced and stable, and then make sure mop any spill water during the experiment to prevent anyone from slipping. Next, the conclusion for this experiment. The experiment is successfully determined that the center of pressure and hydrostatic force on partially and fully submerged in vertical surface. The hydrostatic force is higher in fully submerged surface compared to the partially submerged surface. For the center of pressure, partially submerged surface has the highest value compared to fully submerged surface. It was observed when the hydrostatic force increased with the depth of immersion, while the center of pressure moved closer to the centroid of the surface as immersion depth increased. In fully submerged surface, the center of pressure remained relatively stable due to uniform pressure distribution. The experimental results were close to the theoretical values with minor differences due to errors such as parallax error and slight misalignments in the setup. Finally, the experiment achieved its objective and demonstrated the principles of hydrostatic effectively.